Last time we talked about some fun things, but the entire point of diving into Chapter 8-1 was essentially this idea that, hey, nothing that we are seeing here is actually new. Everything that we have seen so far is things that we have already assessed in one way or another. We've talked about it. Conceptually, there's nothing new going on here, right? There's acceleration in x. Okay, cool. Acceleration in y was 0. Now, acceleration in x and y are both non-zero, but it's the same equations. It's the same kinematics. Nothing that we are doing here is really any conceptually new or novel material, right? It's all just essentially looking at circumstances that we have already roughly talked about, but now we're expanding the cases that we're looking at. So the last couple slides on that one, the ones that I kind of didn't even talk about, kind of breezed over more than anything else. The reason that I didn't care too much about them then is because today is going to be a little bit more of the focus on these things. So these are slides that you have seen before, but they've been some time, right? Like I'm not expecting you to have these things necessarily memorized offhand and everything else. We haven't worked with rotational motion for a little while now, but it is worth talking about these things one more time, remembering. Let me actually start with this one. I think this is probably the most important one to talk about here, because it's essentially showing that everything that we know from linear motion, position, velocity, acceleration, it has an equivalent, a parallel value when you're talking about something like circular motion instead. Now, though, because I'm moving around in a circle and I'm not moving along in some line, we would call our position some angle around the circle. We would call our angular velocity how fast you're going around the circle. And if you have an angular acceleration, then that's whether you're speeding up or slowing down in your rate of going around in the circle. But all three of these things are things that we have more or less seen already. They follow the exact same relationships that we have already seen so far, even to the point that if you wanted to use our kinematics equations, something like delta theta is equal to omega t plus 1/2 alpha t squared, that totally works. All of that is still just fine. It is still kinematics. The only difference is that there are some funkier bits in here that we have to consider sometimes, right? Because the values don't always directly translate over. Sometimes there's a little bit of conversion between the two. But for the most part, conceptually, they work exactly the same, right? And then there's some other things that we can do. We can relate some of these linear components with these rotational components. If you want to talk about something like arc length, which is how far have you actually traveled around the circle, not just a degree, but like your actual distance in meters around the outside of this circle, you can do that, multiply by r. If you want to find the actual speed, not the angular speed, you can do that, multiply by r, right? That's all it really comes down to for both of these. We did have some unique values too, though. We talked about something like the period, right? Or a full rotation or a revolution. This idea that doesn't really have a good parallel in linear motion, because in circular motion, a lot of the time you're seeing the same things over and over and over again, right? In linear motion, if you keep walking in one direction, you're not going to pass where you started. In circular motion, you will. Once you go 2 pi all the way around, you're back at your starting point. More or less. You could technically have stuff like 4 pi, but that's a little bit of a different story. But because we have these slightly unique circumstances, we also have some extra variables and some different numbers that we can talk about for rotational motion, period being one of those. Right? But there's a couple different ways that you can consider writing that out. Now, one of the things that we had in this one, and I had one of the questions on the exam as a bit of a precursor to this. And I know a lot of the time that a lot of people don't like to talk about, it is a personal philosophy that I don't want to throw new material onto you for an exam, not unless you're in like a 600 level course. But because of the circumstances that we are not learning anything new conceptually, that one question where it's talking about the force needed to keep the ball in the circle. Today, we give an official name to that, and that is a centripetal force. We've talked about a centripetal acceleration, and that's the acceleration to keep you in a uniform circle. A centripetal force is the force that's actually causing that acceleration in the first place. Right, so this is an old concept that we're recontextualizing within force now. We said acceleration towards the center of the circle, anytime I'm in a uniform circle, is going to be v squared divided by r, which means that there's also a translation that we can use with our omega just as well. But that is our acceleration necessary to keep us in the circle. And then if you have a tangential acceleration going along the outside of the circle, that is what's going to be leading to our angular acceleration, right? So we've got essentially these two separate pieces depending on which axis you're looking at. We give them specific names because they have different roles. The centripetal acceleration keeps us in the circle. The tangential acceleration, or angular acceleration, the other way to consider it, is speeding up or slowing down going around the circle. So, oftentimes, in these axes that we use, we like to use r, t, and z if we need to consider that third axis. Where might all three of these be necessary? What do we think? Is there a spot that we would consider that, where would we want to look in all three dimensions or something like that? Any guesses, or is it a hard Monday here? Planet? Perhaps, but I don't know if I'd talk about it in quite that way. I would think probably, so even for the case of a planet or spinning something around your head, I would think in both of those cases, I could get away with talking about that as a two-dimensional plane, right? It's spinning in a circle or something else like that. But if I was to think about, and perhaps rotating something around your head is a better one for this, I would think something spinning around on a table would be perfect for this, because something spinning around on a table, the reason that I'm thinking about this, I'm visualizing what different forces, I would need some sort of centripetal force. I'm going around in a tangential direction, and then there's going to be a normal force and gravitational force actually pulling and pushing on that block as well. So all three axes would be necessary in that kind of circumstance. So remember, a lot of the time we can get away with things if we can manage to talk about these things, if we can tilt the axes or something like that to eliminate some of these extra dimensions that we don't necessarily need, that's ideal, but it's not always the case. So I just want to kind of bring that up as we talk about these things. It's not quite X, Y, and Z anymore, now it's RT and Z. But anyways, anytime we are moving in this uniform circular motion that we are so familiar with now, we are set up to have this sort of centripetal force, right? All this is really saying is that whatever force is necessary to provide that acceleration to stay in the circle, that's what we call the centripetal force. Now, there's something a little bit tricky with this, though. And that is that the centripetal force is not a force. Well, it's not a real force, I should say. Let's imagine the scenario. I've got a yo-yo, and I'm spinning it around my head. And this is a hint if you're looking for the correct answer for this question. I'm spinning the thing around my head. What stops the yo-yo from flying off across the room and putting a dent in my wall? Not even force-wise, just the object itself, the string. If I let go of the string, that thing's going to fly. If the string snaps, that thing's going to fly. The string is what keeps the yo-yo in that circle in the first place. The string with a tension in it is providing the centripetal force. And that's the wording that I've been using this entire time. But when I'm talking about something that is a centripetal force, I'm talking about what provides the centripetal force. Because the centripetal force is not necessarily a real force, it is the necessary force that must be provided by something to keep the object in the circle. Right? You can imagine here, has anybody been on that carnival death trap of a ride that's a giant spinning circle? You stand in a giant spinning circle, and then it lifts up and it goes nearly vertical, and the entire time you're kind of like, is this it? Is this the end? Do I have to make peace with myself right now? I love that thing. It's so much fun. It's one of my favorite rides. But they are death traps. They are absolutely death traps. You have to think about it like this. There is nothing in that is there. What forces are actually acting on that, right? Think about stuff like that. What is keeping you in the circle? When you are spinning around in that circle, what is keeping you in the circle? What's stopping you from falling? I want to see if I can find this. I want to make sure that there are no terrible pictures in this as I pull this over. And this is the blurriest picture that I could have apparently found. Maybe that one's a little bit better. But there are things that look like this. There's a small variety of them. So for the most part, I don't know if you can really tell this, but the safety mechanism of this ride to make sure that nobody falls to their death is a very loose chain that they put about 6 inches in front of you. And I assume if the ride slows to a fall, that chain will, like, I don't know, snap you in half or something to make it quick. I don't know entirely why they do that or why they even bother in the first place. But the entire point of this thing is that you don't fall. The entire time you feel like you're being dragged to the outside. Because the ride is constantly trying to twist you around and change your motion. It's constantly providing force on you, and your velocity is always going around the outside of the ring. Right? It's never pointing in towards the middle, because again, if you're trying to point in towards the middle, something's wrong. If you're pointing towards the middle, the ride is broken. And they are supposed to chain you in. I mean, it doesn't do anything. It is like literally a chain that goes like from where I'm indicating and everything else. It's like right here. It's like 6 inches, 8 inches in front of you. It does no good whatsoever. But the entire point of this is that there is a normal force coming from the wall that is keeping you in this circle. You are spinning around. And that means, like, think about what happens, I don't know, like, pull up, like, Roller Coaster Tycoon images or something else. What would happen if suddenly the back broke off? You would fly off in some direction. Your velocity is already such that you've got a pretty significant velocity. You would fly off. The wall being there pushes you back in. A normal force keeps you in the circle and continues to spin around. I mean, I've seen a variety of these things. Some of them have chains, not all of them do. It depends on which ones you go to and how many lawsuits they've faced in the last year. Usually is the big indication. So that is one such thing here. The other thing that I do want to pull up, and the experiment that we like to run with this one is in exactly the same way. Perhaps you guys have heard of this one. Oh, geez. What's going to actually be in my recommendations here? I need to make sure that my recommendations are not actually shown for you guys. So something like this. There's no audio necessary. I'm going to mute it on my end so it's not kind of deafening. He's got a bucket full of water spinning that thing around, and somehow or another, none of that water actually spills out. And normally I would do this in class with you, and it would be the most dangerous day, and you would protect all your laptops, and people would scream, and all sorts of stuff like that. Also, the tiny amount of water in that is a coward's way of running this demonstration. But I'm not going to judge too harshly. For all of those things, right, what's going on there is that the water doesn't necessarily want to fall. As it's spinning around the circle, its velocity is not pointing in that direction, and gravity is actually helping it stay in the bucket at that moment in time because it's helping it stay inside of the circle the entire time. We're going to dive into this a little bit more, and hopefully by the end of today, that whole demo is going to make a little bit more sense. So, let's imagine. A coin sits on a turntable as the table steadily rotates counterclockwise. What force or forces act in the plane of the turntable? So the little white dot is the coin. The big gray disc is, of course, the turntable because, I don't know, I guess they make them in light gray. What forces do we expect to see? Okay, so a small variety. Nobody believes that there are no forces. I think we're all set somewhere between A, B, and C. I'm seeing a couple other answers on that, but I've got a couple tricky things. And one of my big hints for this problem to understand what it's asking me is to look at what's going on here. Two of these are suggesting that there is a centripetal force pulling on the coin. There is not a real centripetal force. Right off the bat, I can say both of these can't be the right answer. The centripetal force is not a real force. It is the necessary force. It is a measure. It's kind of like static friction in the sense of it is saying this is how much force you need to stay in a perfect circle. When you calculate out this centripetal force, when you write this equation, this says if something will provide this much force, then we will rotate in a perfect circle. If something provides more, then we'll spin going inwards. If something provides less, then we'll spin going outwards. Right? Anything other than that, this is giving us a measure, an amount. So a centripetal force is not a real thing, but it does tell us about the number that is necessary from some other force to be provided. Now, that leaves me with a couple different things, and for kind of eliminating these, if I was just looking at the pictures, right, there's really only one answer here, and for context, it is A. But these other ones with static friction, D, I'm a little bit less happy about because that implies that the coin is moving. And once there's kinetic friction in one place, there's not going to be just static friction in other places like that. D's got some issues with it besides that. But B and C, I could almost believe if it weren't for the fact that we are steadily rotating. Steadily rotating to me suggests that we're moving at a constant velocity. If we're moving at a constant velocity or a constant angular velocity, could we all agree that the angular acceleration should then be 0? If I'm thinking about my axes here, if I'm thinking about t going this way, and I'm thinking about r going this way, if there is to be no angular acceleration, then I should expect no forces in the tangential direction either. So there's a couple different ways that we could approach that one, but I want you to be kind of familiar with all of them. First, that centripetal force is not a real thing. It's a necessary measure to keep things spinning around in a circle. It's useful, right? It's very useful to have, and we're going to work with it quite a bit. But it's a concept. It's not a real force that you'll find in the world. Beyond that, thinking about what forces are going to be acting on this thing depending on what's going on, right? We're going to split this up into our two axes here, tangential or radial. Radial is necessary to keep us in the circle in the first place. Tangential is only going to show up if we're speeding up or slowing down. If you don't have a radial force, you're not moving in a circle. Right? That's the big difference on that one. If there's no radial force, you're not in a circle. You're just moving in a straight line at that point. So, I do want to try one of these problems real fast. Let's imagine you're cruising along. A 1,500 kilogram, let's even say cart, drives around a flat 200 meter diameter circular track at a constant speed of 25 meters per second. So what you have just been given is a mass, a radius, and a velocity, not an angular velocity, velocity. Draw the free body diagram of the car. What force is providing the centripetal force? From that, for rubber tires on concrete, you can assume that the coefficient of static friction is 1.0. What is the maximum speed at which the car can stay on the track? And B is certainly a hint for A here. And it would be a sick drift in this picture if only they were actually using the boost properly. But can't have everything. Mario Kart, get out of here. I only play good kart games, thank you very much. But anyways, go ahead and take the next 4 or 5 minutes to work on this one, and then we'll take a look at it together. All right, I think we should probably start taking a look at this. And there's nothing like a hot take on Mario Kart to kick up that course engagement. We love to see it, but at the same time, it is probably pretty distracting from the problem. So we'll use those sparingly. But anyways, one point that I do want to bring up before I dive into this problem all the way. What's wrong with this picture? Why is this picture absolutely not going to be what we're seeing in the actual problem here? Not because the road is slanted. Not just that. I mean, that's part of it. So the car is sideways is an important point, right? So drifting is specifically what I'm referencing here, right? The kind of circular motion of the track at this point does match pretty well and everything else. And aside from the mystery boxes, they don't do anything to the velocity of the cart anyways. But the big thing that I'm looking for here is that we can even kind of see in these streak marks and everything else, right? The tires are distinctly sliding across the road. Static friction is not at play here. It's kinetic friction. But a big part of what goes on with these things is that drifting is a thing that does happen in certain types of races and everything else, right? You don't want to do that necessarily in NASCAR, but there are certain, different series and everything else that will try to utilize a little bit more drifting in cars. But a big part of the reason that you would want to do that is because for certain turns, what you're trying to do is you're trying to say, I think I can maintain a higher speed around this curve by utilizing the kinetic friction instead of the static friction of the tires and tilting myself to try and give even more acceleration in the direction that I want to go. So that is not what's going on here though, right? We are going more in NASCAR style racing where we are just straight tires on the road. But we need to start with a free body diagram. That's always an important part here. So what we're going to have here, let's take this thing and let's imagine we are on flat ground. So I'm just going to draw one single tire here. So let's imagine this is like our one tire on the road. Now, I do need to specify my directions here. That's a really, really important point. So what I'm going to do here is let's imagine that we are turning in such a way that we're going like this. Our direction goes like this. I've got R hat. I'm going to have my Z direction going like this, because in the top-down view, we're seeing something a little bit different. Right? In the top-down view, wherever we're at on this track right now, like here is our cart, for example. If our cart is going like this, then here's our R direction. Here's our tangential direction. So I would say R, Z, and then my T direction goes like this. Into the page is what that means. Into the page. Whereas Z, in this case, would be out of the page, like this. So we've got all of that information so far. We can say, all right, well, this thing should have something like a radius, just regular R, right? Remember that R hat is the unit vector here. But we are given this radius of 200 meters, this velocity of, I have already forgotten, 25 meters per second, and a mass of 1,500 kilograms. So, start with part A, start with my free body diagram. Gravity pulls the cart down. R is 100, R is 100, it's a 200 diameter. Thank you so much. I see diameter and I black out for a second. 100, thank you very much. So, mg pulling me down. A normal force pushes back up. Because I am going in a circle this entire time, if I'm looking at these forces, and I could even do something like this. Let me go ahead and do like a dashed line here to say, hey, this is velocity, this is not a force. I know I need a force to keep me inside. Let me pull this out to a better spot. I know I need some force, some centripetal force, to actually keep me inside of the track, rather than just flying off to the outside. So, go ahead and label this thing in blue. I know there must be something like this. Call it F of C. For now. I know it has to be there. But what actually causes that? Well, I would probably prefer to fly to the outside or keep going in a straight line. So if I'm going to be turning, then what needs to be providing that force is going to be static friction between the tires and the road. This is exactly why when you're going around turns or anything else in cold weather, you're supposed to slow down a little bit, right? This is the reason, because the static friction coefficient between your tires and the asphalt is nearly 1. It's extremely high. That same static friction coefficient, when it gets a little bit snowy or a little bit slick, not so high anymore. It's not 1 anymore, and your normal turns you simply can't make. You will start to slide, and then kinetic friction, even smaller than that. So once you are in the position where you need to recover, that's a lot more difficult by then. So please, be responsible when you're driving around in dangerous conditions and in general. So we've got all these things up, right? I know that the normal force and mg are both going to cancel out, right? Because they're not really doing anything crazy here, but I do need to know that the normal force then is exactly equal to mg. And why do I need to know that? Because I know that in the radial direction, we know that we must have mv squared over r force. That has to be our net force in the radial direction, because that is the necessary force to keep us going in this circle, right? That's the big part here. What's actually providing that force? Well, simply put, it's going to be our static friction. And so let me not actually write out the equation for static friction yet. Let me just write out F of S. Static friction is providing this centripetal force. It is providing the force to keep us in the circle. So, between all of that, we might remember here, and why we're setting these conditions of, you can drive slower than this, but don't go too fast, the conditions and everything else like that, because remember, F of S is a variable force. Variable force. And that means that it's only going to be there as much as it needs to be, right? The centripetal force is going to be the quantity that we need. Static friction is going to try and supply only that much, not more, right? You are not going to suddenly into the side or anything else just because your static friction has suddenly maxed out for some reason. It doesn't work like that, right? Everything that we've seen from static friction so far still applies in the exact same way. So in the premise of the problem, we're asked for the maximum velocity that we can still go around the circle and not crash, right? Not slide off the track. So in a case like that, to maximize speed, first, maximize friction. That is mu of S times the normal force, that is the maximum force that static friction is able to provide, should be equal to mv squared over r. My m's can cancel out just fine. I'm looking for that velocity. We take this thing down, we say v, and I'll even say v max, right? V max is what we're looking at here, not the initial velocity that we had, but v max. In the circumstance with v max, now we're looking at square root mu s times m, not m, mu s times g times r. For a total ending velocity of, where did I put my numbers? There they are, 31.3 meters per second. Static friction and not kinetic friction because the tires relative to the road are not moving, right? It's kind of the difference if we go back, I realize this is a cartoon picture, but it's really the difference of if your tires are sticking to the road, then what really goes on there is that the rubber that is in contact with the road itself is not moving, right? It's supposed to bite into the road and remain there. The car propels forward because that bite doesn't slide. And instead, it starts to lift up, and the forward rubber kind of comes down to layer onto that and then grabs as well and bites. It's kind of the difference of, think about the circumstance when you hit the accelerator too fast in snowy or slippery conditions and your tires just kind of spin out for a little bit. That's an example of kinetic friction because your tires aren't actually biting into the road. They're not sticking. That kinetic friction being much lower means that your tires spin for a little bit, but as soon as they grab, as soon as static friction takes hold again, that's when you get that sudden push forward. But yeah, different types of tires will be set up in different ways depending on what you're going to be using. Like drag tires, for example, are a little bit more low pressure and they've got a lot more flexible rubber because it like tries to layer up. If you ever see a drag race in slow motion, like with the actual drag cars, it's really, really incredible because they'll fold up in a bunch of different ways and you'll maximize that surface area with the ground. You know, it becomes non-circular at the very start of the race. It's pretty cool. The new axes are something. There's it's part of the beauty of the fact that we can always pick and choose whatever we want to have in any of these places, but it does make it a little bit more confusing at first until you get used to that flexibility. It's a nice tool later, but it's kind of like the difference of having, I don't know, like a Lego set with the instructions versus just all of the pieces and you have to build something. Technically, having all the pieces means that you've got a little bit more creativity, a lot more options, but it's a lot harder to get into it at first, unless you've got a good idea of where you're going. But for now, let's try another one of these. And this is going to be kind of in a similar vein, and what I'm going to recommend on this one, I can draw out the axes ahead of time if you would like to see where those would go. I would say probably the best way to draw these axes would be something like Z, R, well, I take that back. I goofed that up. I would leave these as the regular axes, which is going to sound a little bit crazy at first, but the reason is because the centripetal force should point along the middle of the circle here, R. So I would do something like this, and then our tangential goes into the page like that. So, but anyways, let me kind of give a little bit of context to this problem before I just loose you on it here. Let's imagine here, I'm sure you guys have seen this, a lot of different on-ramps and off-ramps for the highways will have a very slight bank to them. Right? Maybe not a ton, but there always is a little bit. If it's going to be curved in some way or another, they will bank the road. And the big reason for that is because it helps provide for that centripetal force, even in conditions where you're either going very fast or the road conditions are a little bit less than ideal. So, if we can imagine here that the radius of this curve is 500 meters, traffic going to be moving in 90 kilometers per hour, which is highway speeds, roughly speaking. So the assumption here is that we would like to set this thing even if friction completely falls away. If we completely lose friction, if the only thing actually providing that centripetal force becomes, well, I'll let you figure that one out. What angle do we need to make this bank to make sure that can happen? And also, draw a free body diagram. That's really important here, right? I've already got kind of a picture shown out here of what I would use to draw for something like this, but I recommend doing a lot of the same. But I'm going to say the next 5 or 6 minutes on this one, and then we'll take a look at it together. All right. So let's go ahead and start taking a look at this thing together. So I'm going to start with some sort of drawing of this thing, and we've got the angle theta and all of that good stuff as normal, right? Nothing new or crazy on that one. The normal stuff as we are used to seeing for things on slopes. The big difference, though, is that now we've got this tangential velocity, and that tangential velocity requires us to have some sort of quantity of centripetal force. So let's draw it. Let's start there. Slope, and we can even go so far as to do like a, how do I have this thing? Draw very quick pictures so that we can actually get some context as to what's going on here. Oh, it's kind of like a car, or like the back tires of a car or something. I'll even, there, now we know those are tires. Perfect. So what forces are actually acting on this thing? Did anybody figure out what all forces we should be expecting to see here? List them off for me. Gravity, normal force. I think I would agree with those two. That all sounds fine to me. So I'll start with a normal force here. I know that the slope is going to be pushing back against the car. I know the gravity is going to be pulling down on the car. And what I'm going to do here is I am going to set a centripetal force. And the way that I'm going to try and draw this thing is I want to draw this thing away from the car to say, hey, this is not a force acting on the car, right? Not in that same sense. I need something here that provides this. I need a net force in this direction to be going like this, right? And let's think about what direction that actually is. That is going in the r hat direction. So I need something there providing that centripetal force, but it's not actually one of the forces acting on this thing. And if I look at my picture, where's that going to be coming from this time around? And remember, no static friction here. We assume that conditions are very, very icy. There is no friction between the car and the road. Right? We have essentially lost control. We are depending on the bank of the road to keep us from flying off, which is usually not an ideal scenario, but this is what things are designed for. But yeah, the x component of the normal force, that's what's actually going to be providing this centripetal force here. And again, if you think about stuff like NASCAR, why do the big curves in NASCAR, why are they sloped to such an intense degree? Well, for this exact same reason. Right? Because then when you're on the straightaway and everything else, you're driving on flat road because that's the ideal condition. As you go into those curves, they're very, very, very steep banks. And the reason they are is so that the normal force can help provide that centripetal force so they don't just fly off into the crowd. Because as cool as it is on TV, it's not good for the spectators there. So that's what we're looking at. I'm given a few different things. I'm given a velocity. And we can even, let's see here. So this is supposed to be 90 kilometers per hour. Can we convert that real fast? That comes out to be like right around 25 meters per second. I think right on, actually. We've also got a radius of 500 meters. And just for the sake of it, I'm going to say the coefficient of friction is 0. No friction at all, right? No static, no kinetic, no friction. So I've got a couple different things going on here. I need to look at what forces I have going along each axis. And let me start with my z-axis, actually. When I'm driving on the road and I'm going on a highway, do I expect to suddenly fly up? Probably not, right? I would hope not, at least. That is not part of my driving plan most days, right? I don't think driving school taught me what to do for any circumstances like that. So I'm going to say that the net force in the z direction should probably be 0. And then if I'm thinking about the net force in the z direction, let me go ahead and draw some of these things real fast. What I would expect for some of these. So something like this, if I do a little bit of geometry, just in the exact same way. Remember how we have seen so many times that if we wanted like this angle right here, then this is theta? Well, in the exact same way, if we were to do that same thing for the normal force, now here, this is theta. The other way that I can rationalize this and make sure that that angle actually makes sense is I imagine what happens if theta goes to 0? Then so too does the normal force point vertical again. Right? They all turn at the same time. So I know that the force in the z direction ought to equal 0. I know that there is the cosine component of the normal force contributing to that. So f of n cosine of theta minus mg. This looks a little backwards, doesn't it? This looks a little bit strange. We're used to seeing the mg cosine of theta, and I know that, but this is a different circumstance. Remember that. Right? In all of the circumstances we had been seeing so far, we had, for one, tilted the axes, But for the most part, we are also setting a lot of conditions about the direction of our motion. In this case, because of the way that the net force is oriented, stuff's going to look a little bit weird versus what we're used to seeing for things. So I've got that equation set out for me here, and then the other equation that I can set out is going to be what's going on in the radial direction, right? So I would say f of r, and I would say, okay, well, I know I'm traveling in a circle, and if I'm not traveling in a circle, then I'm either flying off or something else, and that is exactly what we're designing against. So I need to have a net force equal to mv squared over r, the centripetal force. So what actually provides that? Well, as far as I can tell, the only thing here is actually the sine component of the normal force. Just like that. Gravity's not doing anything in my radial direction. The normal force has a little bit, but not that much. So now I'm looking here. I say, okay, I know V, I know R. The mass, we don't know, but we should make this work for all cars in general, so that's probably not going to show up anywhere. But let's kind of pull back here. We've drawn everything out. We're looking for the free body diagram. We've got that, of course, but we're also looking for what is the angle theta. Solving out for theta. So if I look at my radial equation, I say, hey, there's theta. I don't know m, and I don't know the normal force. Those are all things that I don't know, but if I go up to my equation above, I can say, okay, well, same, I don't know m, and I don't know theta, and I don't know my normal force. And this is a bit of a spicy situation. Because we have three unknowns, and only two variables, or sorry, only two equations. Three unknowns, two equations. That's normally a very bad place to be, but sometimes if you're solving symbolically, you can get away with it anyways. And let me show you why. Because let's take the z equation and rearrange it real fast. I want to solve out for the normal force as if I had the mass. Then the normal force would be equal to mg over cosine of theta. Now what I could do with that is I could plug it in here, and let's see what happens. mv squared over r is going to become mg, should probably write that all on the same level here, mg sine over cosine tangent of theta. M's can cancel out. I don't need to bother about the mass because how much force you need is relative to the mass, and how much force is being provided is relative to the mass as well. So this should work for cars, trucks, semis, whatever you want to put on the road. It should work regardless of the mass, which is, I mean, a good thing at the end of the day. So then we're looking for theta. We need to rearrange just a little bit more then. We would get the tangent of theta is equal to v squared over rg. That means at the end of the day that if we wanted to make sure that we could go at these highway speeds, theta should be inverse tangent or arctangent of that. You should get something like 7.27 degrees. That's all the bank it takes. Not actually that much. So if you ever notice that slight bank, and I guess I shouldn't say that 7.27 is nothing. 7.27 is still a pretty significant incline. But, you know, it's not anything crazy like what you see in NASCAR. Tangent of theta came from the fact that if we're looking at this step right here, this becomes mg sine over cosine. So just combine that into one thing so we can actually solve it. So let's keep the party going. What if it isn't zero? Then you would just have to know what that net force was. But that would be some other unknown, and it's going to be a little bit more of a complex problem at that point. So it is set for zero because that means it's solvable for us in that way. If it's not zero, then we need to know some more information first. But in any case, if you know anything about the net force, you can always say that the net force is equal to everything going along that direction. Right? That is always a very strong starting point for any of our dynamics problems. So one of the other things, if you're going through the reading on this one, is what happens with what we call like orbital speed. This is perhaps a little bit of a strange circumstance. On the International Space Station, if you have ever watched any of the videos of them on the International Space Station, which are very cool videos, by the way, it looks like they are not under the effects of gravity. Right, they're floating around, their hair stands up, water doesn't fall to the ground, it just kind of floats through the air. They have to do all sorts of strange things up there because they don't have the help of gravity like we do on a day-to-day basis. Right, like, when I take a shower, I expect the water to fall down, which is not something that you can take for granted on the International Space Station. It makes it a lot more difficult for a lot of these things. But the reality of it is that they, of course, still feel gravity. The moon still feels gravity from Earth, right? Or else why would it bother rotating around? So they must still be under the effects of gravity, but the reality of the situation is that because they are in orbit, they are constantly in free fall, they never actually feel the relative pull of Earth. Here, Earth is kind of like a basis for us, right? If we jump up, we're jumping up relative to Earth. If we fall down, we're falling down relative to Earth. Things rise up and fall down relative to Earth and relative to that pull of gravity. On the ISS, since the entire thing is constantly in free fall, there's no reference point in that same way. You can't have something falling down because all of it is constantly in free fall. You can't have more gravity acting on something just because it's there, right? At least the acceleration. Of course, the force might change, but the acceleration of gravity is the same for everything, and because it's the same for everything in according with itself on the International Space Station is at zero. So it feels as if they're weightless the entire time. But what that result is, how we actually figure out where it needs to be, is all based on an equation that looks like just like this, right? To be in a circular orbit, which is to say a constant uniform circle going around a planet or something else like that, you need to make sure that you have the right centripetal force and that you are applying by all of the conditions of uniform circular motion. Getting that thing up there, that's a different story. But making it orbit around, it's just first semester physics stuff, which is kind of a neat thing in a sense, right? As complicated as the entire project is, we can pretty well actually predict where it needs to be and how fast it needs to go to make sure it doesn't crash. So how do we actually do that? Well, same way as anything, right? What's providing that force? Well, surely it's gravity. That's why things orbit around when you're talking about things like the heavenly bodies. Gravity makes them orbit around. If gravity is providing the centripetal force, that is to say that the orbit speed should be based on a radius, but it's just square root of r times g. And then you can calculate the period as well. Just like that, knowing the velocity. But this orbital speed is a nice little thing to have on the side as well. Now, what's wrong with this? Why is, if we were to calculate this out for the ISS right now, what's a little bit wrong with this equation that maybe we haven't talked about yet? Does anybody know? Yeah, G is not actually 9.8 at the ISS. G is not actually 9.8, right? We have been setting this condition. I said this very early on, and then we have kind of ignored it ever since then. That the gravitational force, 9.8 meters per second squared, is something that is true at the surface of Earth. The reality of the situation is that it is not actually a constant value. Gravity scales with distance. That is, you don't feel the sun pulling you into the sun because it's really big and exerts a lot of force, right? If you were a lot closer to the sun, of course, you would feel that very, very intense force. But because of the distance away, you really don't care about it too much. Not as compared to Earth, which is relatively much smaller, but because it's much closer, has a much stronger pull on us. So that is a little bit difficult, and that's why they're specifying in here that this is an orbit like skimming along the surface of an airless Earth. you know, kind of a weak approximation as far as it goes. But the reason being is because we haven't talked about how gravity actually works yet. The reality of the situation is that this equation still is true. It's just that G is not quite 9.8 anymore. But it's still most of the way there. It doesn't actually change that significantly. So, let's talk about something else. Something that you can maybe feel. I am sure almost everyone as a kid did this in one way or another, right? You're sitting on the bus or anything else like that, and the bus turns around some curve. And of course, because there's like 5 of you packed into one seat, and you're trying to be as annoying as possible, you like let the pull of it take you into the other person. You smash into them, and then somebody gets hurt and complains, and then you're in trouble. But anyways, what actually causes that? What is that force that you feel? That's something that we refer to as the centrifugal force. This is another not real force. Right? I want to specify that. This is not a real force. This is very much in the same way of centripetal force. The centripetal force is the magnitude of force necessary to keep you in a circle. The centrifugal force, on the other hand, is essentially your reference frame, your pull to the outside that you feel because you're moving around in a circle. And that's a little bit rough. But this kind of explains, like, if you ever go around a turn or anything else, why you feel that slight pull to the outside. It's not necessarily that there's actually a real force there. It's that, relatively speaking, your body, as you feel it, is going straight. To turn that is to exert some sort of force to change that direction and everything else. So the car is going that way. It's got, you know, tires on the road and everything else that are now exerting that force necessary, but your inertia is carrying you forward. It's not carrying you that way. So you feel like this. You lean into it a little bit, right? And that's exactly what we're talking about here. And I know we haven't talked about momentum and inertia and things like that quite yet, but I think you guys have a running definition of those things by now, right? You have been alive long enough to have heard of those terms. But that's roughly what's going on here, right? It's the same thing with the bucket. Right? With the bucket, it's got some sort of inertia. It's got some sort of momentum. It wants to keep going over that way so it doesn't fall directly down. Right? There are forces, and gravity actually helps it stay in the bucket as it spins around. So, concept check here. Let's imagine. A pendulum swings back and forth. What is the correct free body diagram when the pendulum is at the bottom and moving to the right? Relative lengths of vectors indicate magnitude and are important here. Look at it for a minute, think about it. All right, a healthy variety of answers in this one as well. Okay, so let me kind of reason this one out, and let me see if I can get you guys all on the same page with this answer before I have to actually explain it. Think about the forces that are going to be acting in the book. Kind of list them out descriptively, not just with arrows and everything else. I see a rope attached to a book. I'm assuming this is on Earth. So I'm going to start by saying, okay, well, there better be gravity. And every single one of these has an arrow pointing down, so that's probably gravity. I also see a rope attached to the book, though. And I know anywhere a rope is attached provides a tension. So I've got those two. I don't see anything else attached to this book. No other forces pushing on it, no other blocks anywhere else or anything like that. So I know I'm essentially looking for only 2 forces. A third force would require some other object or some other rope or something else like that. So then, let me think about it from there. So I've limited myself. I'm going to say, okay, well, now we're narrowed down to only 2 forces. One of them is gravity. One of them is tension. I need to stay in a circle. If gravity is completely balanced with the tension, what sort of motion would I expect? What do we think? if gravity was exactly equal to the tension, what would I expect to see? It would move in a straight line. That is exactly it. It does have a velocity here, right? We see that green arrow is representing a velocity of the book at this point in time, but if the forces cancel out, then we have no acceleration, then the book is going to keep moving in a straight line. Right? Which you can imagine if you've got like some sort of factory or anything else and something's hanging from a chain, right? That's exactly what's happening. It moves down the assembly line at a constant velocity, but the tension and the gravity exactly cancel each other out. Here, this thing's about to curve up. And that means that I need some sort of net radial force. I know that there has to be a centripetal force pointing like this. And if there has to be a centripetal force, and the only thing going in that direction is the tension, tension has to be greater than the magnitude of gravitational force. And we should expect C to be our answer. If I can go off on a tangent for a minute, actually, before we dive into the material and everything else. I know I ask a lot of questions in the course and everything else, and I ask you guys to participate and everything, and realistically, this is not material that I'm expecting you to have perfected yet, right? That is the point of being here in the first place. Being here in the first place, we're all about learning a lot of this material and exploring this material and discussing things and arguing about why things should be a certain way based on the other things that we know. Right? It's the very loose way of like writing proofs in math, almost. So for a lot of these things and everything else, I think there is a certain learning moment to be had. Imagine the biggest things that you have learned and everything else, I think oftentimes are when either something very significant has clicked after a long struggle, or you have realized that you have been corrected on something. So I don't want anyone to feel discouraged or anything else if they feel like they're not quite getting the answers or anything else. The biggest thing here is that I'm trying to get you to think through what we're looking at in the problem. And then if the description afterwards makes a lot of sense, if then it clicks, perfect. That's exactly the position we want to be in, right? Don't get discouraged or anything else if anything is going wrong with some of these questions. If you feel like you're not getting them before we actually talk about them, that's all right. That's not a huge deal. The fact of the matter is that I want you to be thinking about these problems, and I want you to understand it after we've talked about it. Those are the two big important things to me. But let's look at something else here. Let's imagine a roller coaster car goes through a real sick, and it's a loop-the-loop or loop-de-loop, however you spell it and everything else. I actually had to go around looking up how you spell this, how it's actually supposed to be done, and what I have found is that nobody can agree on the correct way to say this. It's a loop. Rip Vortex indeed, and rip everyone who had to ride the Vortex. Which of the free body diagrams shows the forces on the car at the top of the loop? Ignore rolling friction. Rolling friction is not a big deal for us, right? Assume it's a frictionless track. Two answers so far. We don't even necessarily have to think about this thing as it's going around in a circle. We can simply look at the scenario we've got in front of us and use that. All right. So, here's what I'm thinking. I am looking at the forces acting on the car. If I'm thinking about the forces acting on the car, I see some object above the car. And if I see an object in contact with the car above it, surely there is a normal force between the two. There is a normal force pushing downwards on the car. Similarly, gravity pulls down, right? I don't have a better way to say that one. That's just kind of what happens on Earth. There are no other forces. There's a contact force, and there's gravity. There's no tension, there's no thrust, nothing like that. Those are the only two forces. E should be our answer in this one. And then I think about the different scenarios that this car could be in, right? Let me think about a few different scenarios as we would see them, regardless of whether or not this car is going to actually make it around the rest of the loop. Regardless if this is faulty, if this is like, I don't know, Son of Beast, for example. A very different scenario where the ride does not work as well as it should. What if they go halfway up and then fall directly down? I still expect those two forces to be right there. If it goes around really, really fast, I still expect those two forces to be right there. Regardless of what happens in this loop, these two forces that I see should be there. Because I have a contact force, and anytime I have contact, there is a normal force between the two. And then, of course, gravity doesn't care what we're doing. Gravity still pulls down. And one of the considerations that I want to make here, as we start diving into some of these other problems, are, what about the scenarios where we're talking about, as this thing moves around, what do we have as the minimum speed that it takes to get around? Think about that a little bit. So practically speaking, what's keeping it from just falling? Nothing. Speed. Your inertia as you go around the circle. Right now, we can see this green velocity arrow. We don't want to move down. If we move to the side and into the circle faster than we fall, then we stay on the loop. But if we're not going fast enough, right? Think about those different scenarios. If you don't go fast enough, you get partway up and then you fall. You have to be going fast enough so that you maintain that inertia the entire way around the loop. And actually, I would like to try one of these. Part C in particular is talking about this. What is the longest rotation period that will still prevent lawsuits? But let's talk about this from the top first. Right, so here's another one of these rides, and I'm specifically talking about this one right here. But in an amusement park ride called the Roundup, which is one of the common names for this very common death trap, passengers stand inside a 16-meter diameter rotating ring. After it has acquired sufficient speed, insufficient, usually, it tilts into the vertical plane. Suppose the average mass of the rider is 55 kilograms. Draw a free body diagram of the rider at the top and the bottom of the circle. If the ring rotates once every 4.5 seconds, that is the period, is 4.5 seconds, how much force does a rider feel at the bottom? And what do we talk about? Every single time we talk about how much force does a rider feel, what are we asking about in that one? Kind of like, what do you feel is your relative weight? What is B asking for? The normal force indeed. That is how much force you feel. And then finally, what is the longest rotation period? What is the slowest that we could be going that will still keep people in the ride from falling out? I'm going to say take the next 6 or 7 minutes to look at this one. And I'll step in here in maybe the next 3 or 4 and draw out what I imagine to be my free body diagram, and that way we're just all on the same page. But anyways, go ahead and get started on this. Think about this. Remember what goes on with normal forces. Remember what goes on with gravity. Think if there's any other forces or not. Go ahead and get started. All right, so I want to start. Let's draw out this free body diagram real fast, and let's make sure we're all on the same page with that, just to make sure. If you feel very confident in this thing, go ahead and keep working. Just keep an eye on this just to make sure that we're all on the same page here. But as I'm thinking about this thing, we're in a really big circle, something like this, right? And of course, here is our person on the bottom. Here is our person on the top, right? As normal human people are typically drawn. If I think about what's going on in the very bottom, right? I see, hey, gravity should be pulling down. I would agree with that. Hey, a normal force should be pointing perpendicular from the surface. Kind of like this. On the top side, I say, hey, gravity should still be pulling down. Hey, there is now a surface above us, so the normal force should also flip direction. Can call this my direction of rotation, call it omega or something else like that, just to make sure that that's all clear on that one. And then our radial direction will depend on which of these we're looking at. But if we're only looking at the top and the bottom, the radial is the y-axis as far as we might be concerned. I'm a little bit less interested in that one right now. But that's what I'm thinking for a free body diagram. Let's keep working for the next 4 or so minutes, and then we'll take a look at this together and solve it all the way through. All right, I think it's time to dive into this one. So, I've already got my picture drawn, which is very nice. I already have a radius and a mass, and I'm told some sort of starting period for this thing. So let's go ahead and draw out some of this stuff so far, and I might have a split for this for part C, because some of these variables are going to change. But I'm given radius, 8 meters, mass, 55 kilograms, capital T period, equal to 4.5 seconds. Okay, so I need to figure out first, how much force does the rider feel at the bottom? That is, what is the normal force the rider experiences at the very bottom of the ride? So let's zoom in on that part real quick, and let's say, okay, well, we've got a normal force pointing up, we've got gravitational force pointing down, but we know that there must be a centripetal force pointing towards the center like this. That is the net force that we have to actually stay in the circle. If we have anything other than that, again, something's very wrong. In some way or another, something is very wrong if we don't have exactly that centripetal force. So let me kind of roll on that idea. Let me say, all right, well, the force in the radial direction, F of r, must equal that centripetal force mv squared over r, should be equal to the normal force pointing up. Gravitational force is trying to stop us from being in that circle. Not a big fan of it. So then, if we're looking at just the normal force, well, this is easy. The normal force, then, should be equal to whatever it takes to keep us in the circle, plus whatever gravity is trying to take away from that amount. And that's it. For a total of 1,396 newtons. How do we feel on this so far? How did I get V? I should have probably actually shown that, shouldn't I? That comes from T. Sorry. The way that I can do that one is I can say, all right, well, there's a couple different ways that I can consider this. T being equal to the period, please. There we are. T being equal to the period should be equal to 2 pi r divided by V. That is my definition for the period on this one. So I can rearrange this and I can say, all right, well, if the distance divided by the velocity is equal to the time, then the distance divided by the time should equal the velocity. So that's how I found my V. Sorry for that one. I kind of just skipped right over that, didn't I? And I should find, if we're plugging in numbers for this thing, just to make sure we're all on the same page, I should have gotten... Just thinking about it. Got to get those drivers. There we go. 11.17 meters per second. All right. Are there any other questions on this part so far, though? And this is for the bottom specifically, right? Because that is the, how much force does the rider feel at the bottom? Okay, so for part C of this one, this is a little bit more complicated, and I've got to kind of go through a line of arguments to convince you of the conditions that we're looking at here. So first, we want to avoid lawsuits. Goal, avoid lawsuits. If I'm trying to avoid lawsuits, which part of the ride do I need to be most concerned about? I'm going to argue probably the top, right? Because arguably the bottom here, if the steel of the bottom falls through, that's a manufacturing issue. We can push that blame off onto somebody else. Right? But if they fall off at the top, then that is certainly an operation error. So we need to be focused on what's going on at the top here. Now, we're looking for, when we're saying what is the longest rotation time, that is saying what is the slowest speed this thing could rotate around and we would still be safe. People could still stick to the top. So let's think about it like this. I want to go back to these ideas of what happens when you take a turn too fast and you feel that centrifugal force pull you really far to the outside. What happens when you spin that yo-yo around your head really, really fast? What do you feel? What happens then? What goes on with the forces? Think about like the difference if I was to go around a curve at 5 miles per hour versus at 20 miles per hour. What kind of differences do you feel? One of these, the 5 miles per hour, I would expect, maybe I feel a little bit of a tug to the outside, but probably not. If I'm closer to 20 miles per hour, my girlfriend's going to yell at me and something in the back of my car is going to slide and break. The difference here is that the faster you go around, the more intense that centripetal force. That centripetal force, right, there's essentially a combination of things playing into this. The faster we go around the outside, the stronger the normal force is going to become because gravity isn't going to change. Right? The mass of the person is not going to suddenly change, shouldn't hopefully change while they're in the middle of the ride. That's got some implications that we're going to avoid right now. The mass of the person on the ride should not change while they are on the ride. Gravity should be a constant force. The normal force is variable. It's allowed to change. It's allowed to get a little bit larger, a little bit smaller, depending on how fast the ride is spinning around. That is to say, if we were to spin this thing around faster and faster and faster, we would expect the normal force to increase to provide that full centripetal force. What about in the opposite direction, though? Could we all agree, then, that if I start moving this thing slower, we would expect that the normal force would get smaller and smaller and smaller and smaller? What's the smallest that the normal force could possibly be? Zero. The normal force being 0. Gravity, the acceleration from gravity being 9.8 is a constant regardless. That is to say, though, that the smallest the normal force could possibly be is 0. And at that point, gravity is the only thing providing some sort of radial force. What did we say would happen if the force actually felt exceeded the centripetal force? If the force actually pulling on us exceeds the centripetal force, that means we're falling in towards the middle. We're no longer avoiding lawsuits. Then we have lawsuits. That is to say, our sweet spot, the bare minimum that we can use to get around this whole thing, is the condition where the gravitational force at the very top of the ride is providing just enough force to keep us going around in the circle, and no more than that. Normal force is cut out, but we are not moving so slow that the radial force pulling us inwards exceeds the centripetal force. So if our goal is to simply avoid lawsuits, what that is saying is that the centripetal force must be strictly greater than or equal to mg. If it's equal to, we are dancing on a very fine line. Right? We are dancing on a very fine line at that point. But as long as we are in one of these conditions, right, to make up that difference, if the centripetal force is greater than mg, it's normal force that's there to help make up that difference for us. So with that in mind, this is the condition that we need to satisfy, but let's look at that radial direction. We know that there should be a centripetal net force regardless. Contributing to that is going to be the normal force plus mg. And why have I drawn all these things plus? Because remember that the radial axis always points towards the middle, like that. So centripetal force, gravity, and normal force are all positive quantities in this case. So this is my complete expression. This is my net force in the radial direction, should be equal to this, all of this. We have set the condition. We are moving at the minimum possible speed when the normal force has gone to 0, but gravity is just enough to provide for that centripetal force. We would like there to be a little bit more normal force because that's safer, right? The more normal force there is, the safer we are on the ride. But like this, this is our bare minimum. So then, we're looking at this in much the same way. We're asked about a time to find. That velocity, we know will relate to the time. So let's use this to solve out for velocity. First, I'm going to say v squared over r is equal to g. I can cancel out those masses. So it doesn't matter who is on this ride. Everyone should feel the same force, more or less. And then from there, we would say, all right, well then v is equal to square root of r times g, or g times r. Which, wouldn't you know it, is our orbit velocity. Convenient thing on that one. But in a very, very different context, right? It's not nearly the same thing in this case. So with all of that information, we find that the minimum speed that we have to be traveling, our tangential speed, I should say, right? The velocity should be something like, not that, 8.85 meters per second. That's how fast we need to be spinning around. And if we translate that into the period, it's supposed to be equal to 2 pi r divided by v. That means the minimum time, or the maximum time, I should say. The maximum time for that period is 5.68 seconds. So the very last problem here is actually very short. This is where I would have placed the demo itself. But the very last problem here is what happens if I were to swing the bucket around, and my arm is, maybe you can estimate, like between my arm and the bucket and everything else, it's about 1 meter long. If I swing it in a vertical circle and no water were to fall out, how many rotations per second would I have to be making to make sure that everyone actually stayed dry? Let me run through it real fast. But it's much the same thing. If we're thinking about what's going on in, and I can even just draw it on this one, right? Here's our bucket filled with space water. Filled with space water like that. If it is moving around in a circle just like this, and let's imagine that it's got like an omega that looks like that, then in much the same way as before, I am looking at the circumstance, the water falls out of the bucket when gravity is the only thing, and it's not moving fast enough to go around the circle. If I swing it faster than that, then there is going to be gravity and normal force both acting on the water. So I would expect gravitational force. I would expect normal force. We keep setting this condition. When we're talking about the minimum speed to get around a loop, that is the condition where gravity is exactly enough to provide that centripetal force and the normal force has gone to 0. Any faster than this, and the normal force shows back up as a real value. So then, same solution as before. I get something like this. I can solve this out in exactly what we had just found for part C. Why the normal force points down? Because that is, if I'm looking at the forces acting on the water, that is the force of the bucket on the water. Or the other way to think about this, if you're looking at like the bucket, whether the bucket would continue going in the circle, I'm more focused on the water because that's the thing that actually spills out if I mess this up. All of this stuff. Is angular speed already in RPM? No. Our natural units for omega are radians per second. So there's a conversion that we can do for this. But the time that I would find for this thing would be something like this. I would say 2 pi r over v That is, once every 2 seconds, I have to spin my arm around. If I want to flip this into revolutions per second, then I just say 1 over t. And in fact, the reason I bring all of this up in the first place and what we can do with this is that if we go back to this video, seeing the demonstration of this thing as it spins around, let's take a look at the speed here. It's right around a little bit faster than 2 seconds because the 2 seconds is the minimum speed. So if you're being safe with this thing, then it's much preferable to do it just a little bit faster just in case. But that's just kind of a quick run through on this one just because it's exactly the same as what we had just seen in part C. But also we're kind of at the end of time anyways. Oh, I probably should have actually converted that to RPM, shouldn't I? That's 4.98 revolutions per second, but you need to multiply by 60 to actually put this thing into a revolutions per minute, don't you? .88 RPM. But that's all I've got for today.